Okay, so caching, bit of history. What's the best way to describe the history? So
this isn't exactly a light topic though either, is it?
I'll try and, yeah, I'm going to try and make it, it's anything with caching is not light. So it's a shame, I guess, but okay. So if I go, just make a class, a.x. So if I just do, so this, if I do anything like this a.x here, I'm looking up the value x in the class A. And the code, the byte code is printed up here. So it loads A and then it loads the attribute X from A. This is a very common operation in MicroPython to subscript things. You know, if you do any class like machine.I2C, it is going to do that kind of lookup, and or time.sleep or anything like this. You have to look up the variable, the name in the entity. So that entity could be a module, like on this last line, or a class, or a module here, or it could be a class, or it could be an instance of a class. So if you do I2C.scan, that's looking up an instance of a class. Scan is looked up in the instance I2C. So lookups are very, very common in Python, and they are dictionary lookups usually. But they're kind of, if they're the crux of Python in that most of the speed, well, most of the operations that you do end up hitting a dictionary lookup at some point. So if you can make dictionary lookups fast, Python will run faster, and MicroPython. So that's the general idea, is to make lookups fast. And the way you can do that is with a cache, and a cache in this case remembers any previous lookups and is used to shortcut the lookup. So whenever we have to do a lookup, say time.sleep, we've got to search through the time module for sleep. And if we find it at position 10 in the dictionary, we can remember for next time that start looking at position 10 when we're looking for the word sleep in the time dictionary. And if you hit that immediately the first time, it means that you don't have to look anymore. So things will be much faster. So that's the general idea of caching when you're looking up in dictionaries. And MicroPython did have an optimization for this, where in the bytecode, whenever you had a load, like this load attribute of X, there would also be a byte in the bytecode, which would be used to save or cache the previous successful lookup. So when that bytecode was run a second or third or fourth time, it would remember the last location it looked for that bytecode, and it would try again in that location. And usually it would be a hit, and it would be really quick to look up. So the first lookup would be slow because it would miss, and then it would remember for the next time, and it would store that value in the bytecode. So the bytecode was self-modifiable in that sense that there was four operations, four different opcodes which had this property where they would cache or remember their last successful lookup. Now that was really successful, but the problem was that it was only enabled for the Unix port because it means that bytecode has to be modifiable, which is not really good when you have bytecode frozen into ROM or flash memory. So this optimization is not really compatible with bare metal microcontrollers that for the first, well, in some cases have frozen code. In other cases, you don't want to use so much memory to have a byte for all these opcodes set aside just for the cache. So it was never enabled on bare metal targets. So only Unix could really benefit from it. And also when you have native code, when you do at micropython.native, this kind of stuff, that also can't take advantage of this caching because the native code generator just didn't do that. Didn't do caching. It's just hard to do because native code doesn't have space to sort of store stuff in it. So what we've done, Jim did the sort of the final, well, the most of the work in the end was to change the way it was done in the old way to a new way. So it's the same concept, just caching, but the cache is stored instead of in the bytecode. The cache is just stored globally as a single global cache, which is a little bit of memory that tries to remember previous lookups. So we've removed the caching, the inline bytecode caching, which is what I've been describing. We've removed that and replaced it with a global cache for all functions. And so that the advantage of the global cache is that it works with all lookups, even normal dictionary lookups when you just use a dictionary, not just a few special cases like loading from a module. It works with native code. It works with code that's stored in ROM. So it's really good in that sense. It uses less memory because you just, or a fixed amount of memory, you just say, okay, I'm going to use 128 bytes to store my cache. And so no matter how many modules I'm loading, it's only going to be 128 bytes of cache. And it also means now that the bytecode that we compile for the Unix port and bare metal ports can be the same. So before this change, when you use MPY cross, I think this is probably an old version. Oh no. There was an option to MPY cross, which was this cache lookup bytecode. So it would generate different bytecode when you turn that on, so that it had a slot to store the cache. But now that option's gone, which means bytecode is much more uniform across all the ports. So this is like one thing to realize in the next version of MicroPython, that this option has been deleted. It usually just means you have to recompile any MPY files, but only if you were using the Unix port. All bare metal ports stay the same. But they now have a huge speed boost because we've enabled this global cache for we've enabled
Jim.
this. Yeah. No, Jim's on the call. Yeah. So we've enabled this global cache, so all of the ports can benefit from it.
You mentioned that the cache was a fixed size, or can that be altered per port or even per board per port, like for boards that have a stack of RAM? Is there any benefit for that?
Sorry, so yeah, you can enable it for boards that don't have much RAM. But sorry, so ask it again.
No, I was saying that you said that the global space you've got is a fixed size, right? Is that settable per port?
Yes.
Per board?
Yes. So I was going to show you the actual commits that we're doing this.
Okay, cool.
So yeah, so here is the feature that Jim added. It's quite small. It's quite neat. I'll just see where the option is. Yeah, so here's the option to turn on MicroPy Optimat lookup cache, and the option that controls the size, which just defaults to 128 because from testing that showed to be a good value. Much more than that doesn't give much of a boost, but I guess for larger programs it could, because you want more things to cache. And so yeah, here's the actual cache. It's just an array of bytes. So you can adjust that per board if you want. And there's a whole bunch of performance tweaks you can use to measure the optimization, but it can be tough. It really actually does depend heavily on the architecture, like RISC-V or Extensor or ARM. And even on ARM, it depends if it's a Cortex M0 or M4 or M7. So it's pretty, yeah, fine tuning it is quite hard, but in general, the options we've chosen as the defaults work quite well. And it really only boils down to this single sort of piece of code, which is whenever you're going to do a lookup in a dictionary, you look up in the cache to get the index to start looking at, or just the index, and you check if the key at that index, so like the key in this case is the word sleep or something, which is what you're looking up. If that's equal to the index you're looking for, then just return immediately. So this is the crux of the optimization, is just if this place we're going to look in is exactly what we want, return straight away because we've found it. So there's no sort of like function call to check if it's equal. It's just if the key is equal to the index, which is usually the case for a Q string or an integer, just return the slot. And if it fails, continue and do the lookup the normal way, which is the slow path. But this is really the thing that will return. And this gets hit a lot of times. You get it's surprising how well this does. Well, maybe not surprising, but it does very well. Sort of the trick also is how you compute that sort of initial guess for where to look. And because it's a global hash table, it means that two different parts of programs are going to be using the same table. So they may have collisions, or actually they may share it. Because if two different parts of the programs both look up time.sleep, which will be probably quite common, they can both benefit from the same cache access. So computing that cache offset is actually computed as it's quite simply just uses the index here. I think that's what we tried many different things, like a combination of a pointer to the map plus the index and other things. But in the end, it looks like mpcache get mpcache entry. So look up cache offset of index. So the index is the function. Yeah, you just take the index, which in this case is like the pointer to the string you're looking up, or the Q string. So if you're looking up time, it basically takes the word time and what the pointer to time, and just shifts it right by 2. So it's a very simple lookup, but it works very well. So different words will be unique, but words that are the same, like right, if you look up right in 2 different dictionaries, that will give a collision. But in general, this is going to work. It's going to work quite well.
What happens in a situation where it's the same index, the same word, but it's not from the same thing?
Yes. So it could still be by luck or by chance hit the right entry, and then that's fine, because if you hit the right entry and look it up and it's the right key, you've found it. There's no error if you've found the entry with the right key. But in the case where it misses, it will fall through and go to the slow path. But there will be potentially contention between different bits of code that are both using the same word but in a totally different dictionary, and one misses and then it updates the cache, and then the next one runs and it misses and it changes the cache, and they go back and forth. So they'll both fight for that slot in the cache. So that's probably the worst case scenario.
I was talking about more something like you used the example sleep, was if I had a class and then had something in it called sleep. Like,
yes,
so time sleep, and then there's something else dot sleep, and there's something else dot sleep.
Yep. That's what I mean. That's the case where they can fight for that location in the cache.
Oh,
because the word sleep is the thing that's looking it up.
Right.
But they won't.
Okay.
So they won't give an error there won't be an error in the lookup, but it'll
just miss and then have to go and find it.
It may miss and then have to go and find it. Yeah.
Okay, I got it. Yeah.
So
this.
I was just going to say there's a slight optimization case for avoiding the name collisions even in separate namespaces.
there is currently no optimization for avoiding the collision there. One way to do that would be to add the pointer to the map you're looking up to find the index.
Yeah, I was
so
more
that-
thinking in the user space. If a user writes their code to specifically avoid those collisions, that will make the code run slightly faster.
Yeah,
That's true. Yeah.
Yeah. Okay.
But this, I mean, this is really going to optimize a tight loop, which is the thing that needs to be optimized. Code that just runs once can't benefit from a cache, and well, usually it doesn't really need to, because if the code runs once, it doesn't matter that it's not running fast. The code that you to optimize something, you usually want to speed up the hot spots, the code that's executed many times over, and that's usually a loop. And if you're in a loop, the first time through the loop it might be a bit slow. It will warm the cache up, and then the next time it will get hits in the cache. So yes, our benchmarks, we have a handful of them. You can see them there in the repository. They don't cover all cases, but all of the benchmarks we had were improved by this optimization.
So can I just ask, just in terms of the scope of it all, so like something like the NeoPixel class, so you go pixel equals NeoPixel dot NeoPixel, whatever, blah, blah, blah. Every time you then reference NeoPixel pixel with a, an index to be able to set a color, but that's going to go and hit this every time to find pixel to be faster?
No, because in that case, if I understand what you mean, like you're doing NeoPixel 0 equals 1, 2, 3 sort of thing, right?
Yeah.
Is that what you mean?
Yeah.
Yeah, so there's no real dictionary lookups there. I mean, it's probably looking up the dictionary to find NeoPixel object, NP in this example.
That's what I'm saying, but every time, so if you're in a loop and you're, let's say you've got 100 pixels and you're in that loop setting NP, 0 to 99 every time you call NP.
Yeah, so it depends. If it's in a, if NP is a local, there's no optimization because it's looked up immediately and it knows the index of NP in the locals table. But if NP is a global variable, then yes, it will improve that case. So if I have a loop, yeah, what I said, it depends if NP is a global or local variable. For a global variable, it will definitely improve that case.
Okay.
Yes.
Because like that's the common practice, like when you look at all the examples and all the examples I ship with my code, it's just a flat file, a main.py, it's just a flat file, and you declare a whole bunch of variables at the start, and so they're global, right?
Yeah,
and
that's
at the end of it, you've got a while loop that makes the the APA or the pixel cycle colors, and you're constantly in that loop setting the color by calling the pixel, right, the variable. So in that case, there would be improvements from that.
That's right. That's right. Exactly. Because when they're all global variables, and so every global variable there is going to be different. So it's going to have its own independent spot in the cache, maybe, but modulo the cache size, obviously.
Yeah. Okay. Cool. Excellent. So
it's the big. I don't want to go on for too much longer, but I mean, so as I said, we have a test suite and we've tested a lot on the test suite, and the test suite was improved compared to the old caching that we had. And obviously, maybe there are other things we can improve with different performance tests, like when say you have two streams that both use write and they're actually different write methods, maybe that will that needs something to improve that. But one of the big things to note was the simplicity that was gained by removing the old option, which is this commit here. This has got a long discussion here about the improvements in performance improvements, but removing this code was something I wanted to do for a while, because you can see all these red minuses here, which was nice, just because it added so much complexity to the compiler and to the generated bytecode, and having bytecode over Unix and bare metal different. It was a real it was a pain. So hopefully this improves sort of usability now. So you can see all of this stuff's been removed, and the bytecode is much simpler and uniform now. So these were the options that originally had these were the bytecodes that originally had a cache byte associated with them. So I'm quite happy that that's been simplified, and it's been sort of a few years ago, Jim and I discussed doing this, and it wasn't really a top priority, but now it's been done. There was another optimization that Jim managed to do, which also helped improve things, which was adding a fast path for this load attribute opcode in the virtual machine, which, yeah, it's just a bit of code here, which optimizes the common case of looking up an attribute in an instance. So like neopixel.write, for example, or I2C.read into, or read from into. So this also added maybe 10% speed improvement for certain performance benchmarks. So that's what I wanted to discuss, really. So there's kind of three things. There's this fast passing of load attribute, the cache, global cache, which is now usable on all ports, and the removal of the old one to simplify things. They were the three key parts there. So I think I'm not sure, I think only STM32 has currently enabled that, but we're looking to enable on other ports after we've benchmarked them. Yeah, so it's not on an ESP32 yet.
You mean just the load attribute fast path is not there?
No, none of them.
Oh, none of them are on me. Oh, I was going to try it tonight. Oh.
So it's just a single option. You can see you just have to enable this thing.
Right, so if I enable that, it'll work.
You enable these two things, load attribute fast path and
okay.
cache. But the problem with ESP32 is that it's hard to benchmark because the cache, the ESP32's instruction cache, it really messes with optimizations if you from one run to the next, but one build to the next. Sorry. Yeah, you have to take it with a grain of salt sometimes.
Right, but the bigger the application and the more parts of the application, right, and the more, yeah. I mean, I've been chatting with Matt recently, just about the speed of stuff. Like in MicroPython, the ESP32.
Yeah.
And like I could see, I mean, so with if for whatever reason the lookup cache fails, like if it's a miss and it's got to go and find it anyway, the worst case scenario is it's going to run as slow as it did before. It's not really going to be much slower.
It will be a tiny bit slower because it has to first go through the caching check.
Right.
But
right.
the caching check is very quick. And I mean, yeah, what we've shown you now, benchmarks.
Like that would be quicker still than missing stacks in the dictionary till it finally gets it, right?
Yeah, that's right.
Okay. So okay.
Sorry.
I was going to say, look, I'm really keen to give this a shot. Like I'm struggling right now with my Reflow Master code. I'm currently 50-50 where I've started putting it back into Arduino because I need to ship it, and it's like just so much faster. Like it runs as an application for the user. It's so much faster, but it's just a disgust. I feel disgusting being in there developing it, and I've got so much really cool code on the MicroPython side that I just can't port over because it just can't do the stuff I'm doing. Like I'm really fighting to stay in MicroPython on it, but it's not as nice a user experience because of its performance.
Yeah,
and I mean, and some things that's a whole different discussion about, but stuff like this could generally make it faster. Like I do stacks of lookups for my font rendering because I'm doing my own custom font rendering. So I need different size fonts and different colors, and I'm caching them all myself, right? In a dictionary, but then those indexes, I would assume, maybe, I don't know, I'd have to look at how I've done it. Like, yeah, okay. I mean, I might be able to rewrite that to work in a way that
benefits from this, yeah.
Benefits from this, yeah.
So if you're gonna, maybe we can talk about this later, but if you're going to look into it, as I said, the ESP32 caching of instruction cache, as in the hardware level, has a real impact. And what you can do is you can try one build, and then you can try a build with computed go-to enabled or disabled. Enable and disable this option and see which one's faster, and just stick with the one that's faster. Let's talk about this separately.
Yeah, okay, sure. Sorry, didn't mean to hijack it.
We can make, I think we can get like, yeah, we can have a look.
Did you have any like results you can share from your benchmarks from STM32 in terms of performance speedups?
It's all on the GitHub issue, but of course that's easy to say, but these are sort, no. I mean, yeah, I'd have to look at the GitHub issue. I'll see if I can find it and post it to the chat.
Cool. Thank you.
Anyway, so that's all I wanted to say. I'll see if I can find the GitHub issue while we're waiting.
It's really exciting.
Yeah, I'd be really interested to see because you see on your code is obviously a real life example. It'd be really interesting to see if it's a noticeable boost.
Sure.
And then we can understand. Do you have SpyRAM on the thing that you're using it with?
I do. And
you see,
now,
that could be that if you really need all that RAM, you need it. But it could be that reducing the amount of RAM available with MicroPython might improve the speed, because it doesn't.
Well, I've ported it to the S2 now, so I don't have any of the performance issues on PSRAM like the original ESP32's got. But the S2's also got less SRAM, way less SRAM. So I have to use the SpyRAM. But it's I've already done that change, hoping that I'd see a noticeable difference, and I didn't see anything. So yeah.
Right.
But maybe the S3 is an option. Like yeah, and that's got 512.
Do you run it at maximum speed?
I am. Yeah. I'm running at 240 megahertz, and like I'm clocking the screen, like the SPI bus at 80 megahertz, to try to get the much out of the screen as possible. Like yeah. I mean, there's other issues, like, I mean, a lot of my performance stuff could be solved with a native display driver, but that's less likely to happen right now than getting a boost out of the caching stuff.
Yeah. Okay. Well, I mean, you can expect to get 20-30% improvement in some scenarios.
Wow.
It really highly depends.
Yeah, grain of salt. Yeah, all good.
All right. So that's that. Anyway, Matt, I think I'll hand over to you.